In chapter 6, we're going to go through a bunch of specific methods of doing inference based on the parameter that we're interested in. So chapter 6.1 is about a single proportion, and the book has little subsections for each of the sections. So chapter 6.1 has sections 6.1d, which is about a distribution. It has 6.1 ci, which is about a confidence interval. And then it has 6.1 HT, which is about a hypothesis test. And as the book says, you can think about these in any order. They don't have to go in that order. I'm going to try and be consistent in the way that I'm ordering my material so that we're going in the same order as the book. So we're going to start talking about the distribution, the sampling distribution for a single proportion. Before I get into just giving you the formula, I want you to believe me that the formula is something that can be proven by statisticians. So it's something that didn't just come out of thin air. I didn't make it up, but it is a real sort of property, and that it's a good approximation of the sampling distribution that we want to approximate. So this derivation is not something that I'm going to test you on, but I do think that it is useful to think about. And it's going to call back to the stuff that we were doing in chapter P when we were talking about probability. So I'm going to tell you about something called a Bernoulli random variable. And a Bernoulli random variable can only take on two values. It could be 0 or it could be 1. And we're going to think about the mean and standard deviation of this random variable. So we have talked about the way that you compute the mean of a random variable. It could be E of X, that's expectation of X, or you can just say it's equal to mu, and that is the sum from I equal 1 to n of X sub I times P sub I. And those x's and p's are going to come from a probability distribution function. And the way that we make those for a discrete random variable is we make a little table. So I'm going to put in my table the value, which is the x, and the probability, which is the p. And there's two possibilities here. My value could be 0 or it could be 1. And these two possibilities have probability p for 1 and 1 minus p for 0. So that probability could be 0.5 if it was flipping a coin, or we could set it to be some other probability if we were interested in a different proportion there. So then if we think about the expected value of x, that's going to be each of the individual x's. So I'm going to start with 0, x sub I times the probability of that thing happening, 1 minus p, plus the next x, which is 1, that's the other possibility, times p. And then I can just work through the math. 0 times anything is 0, so I can just cross that out. And so the expected value of this random variable is p. And that kind of makes sense. We would expect the probability to be the expected value. So if you flip a coin, you're expecting to get sort of like half ahead because that's the way expected values work. I'm just going to move some things around so that I have a little bit more space here. Okay, so now that we have our expected value, which is our mu, we could find our standard deviation of our random variable. So I can say sigma squared of x is going to be equal to, well, again, it's a sum, I equal 1 to n of x sub I minus mu of x squared times p. So again, I have to think about what my different possibilities are. My first possibility is 0 minus, and then what is my mu sub x? Well, that's p. So 0 minus p squared times the probability of that thing happening, 1 minus p, plus, and now I'm going to have 1, my other possibility, minus mu sub x, which is p, squared, times the probability of that happening, which is p. And so now I can do some algebra and expand this out. So let's see, 0 minus p squared is p squared, 1 minus p plus p times 1 minus p squared. So let's break this piece out. 1 minus p times 1 minus p. We've got 1 times 1 is 1, minus p minus p plus p squared. So I can write this again. I'm going to do the distribution here. P squared minus p cubed plus p times, and then I'll just do some combination. 1 minus 2p plus p squared. Then I need to do just a little more distribution. P squared minus p cubed plus p times 1 is p minus 2p squared plus p to the third. And then I can cancel some things. So I've got a p cubed and a minus p cubed. That's good. Now I've got, let's see, p minus p squared, because I had p squared minus 2p squared. And then I could distribute that back out and say that's p times 1 minus p. So now for a Bernoulli random variable, I have my expected value, which is p, and then I have my standard deviation, which is p times 1 minus p. So I'm about halfway there to my formula. So the next thing I'm going to tell you about is a binomial random variable, which is a linear combination of Bernoullis. So if y is a random variable, so if y is a binomial random variable, then the mean of y is going to be equal to n times the expected value of x, because it's a linear combination of a bunch of little x's, which are my Bernoulli random variables. And so I can just say it's n times p, and then the standard deviation for y is going to be n times p, 1 minus p. And this would be as if we had flipped a bunch of coins and then we were counting up how many heads we got. That's almost what we want for a proportion. But for a proportion, we actually want the binomial situation for a proportion where our p hat is going to be equal to y divided by n. So that's the number of successes divided by n. And then I can say I want to find the mean of the random variable of p hat, and that's going to be the expected value of y over n. And I can pull out that 1 over n, so 1 over n times the expected value of y. And then I know the expected value of y from up above. This is the expected value of y. So this is 1 over n times p. And then my n's are going to cancel, and my expected value is just p. So that's great. If we have a proportion, our expected value is that probability. And then the other thing that we need is the standard deviation. So we're going to do the standard deviation of p is equal to the variance of y over n. And if I want to pull out a constant from a variance, I need to do 1 over n squared. I need to square it times the variance of y. And that's going to be 1 over n squared times n times p, 1 minus p. Then one of my n's is going to cancel. So I can cancel that squared with that n. And now I have p times 1 minus p over n. Then the very last piece of this is the square root of the variance is equal to the standard deviation. So we want sigma of p hat, and that's going to be the square root of p 1 minus p over n. That's probably the most important thing here. So we've just shown that if we want to have the standard deviation of a distribution of proportions, that's going to be approximated by the square root of p 1 minus p over n. And there's this thing called the central limit theorem, which says that as n increases, the distribution converges. So I've done a few simulations here. So in this first row, this is p equal to 0.1. So if my proportion was 10%, and I did samples of size n equal 1, I would get this very weird looking distribution over here, which does not look very normal at all. But if I increase the sample size to 10, well, it's looking a little bit better. To 30, it's looking a little bit better. To 50, it's a little bit more normal. And then once I get to 100, the standard deviation is very small. That distribution has pulled in nice and tight. And then I could do the same thing with p equal to 0.5. If I just take samples of size 1, even if I do it many times, I'm going to get this strange distribution. But then as my sample size increases, my distribution is going to become more normally distributed. And the same thing with p equal to 0.7. As the n increases, the distribution looks more normal. So this all leaves us with the idea that if n is large enough, then we can approximate p hat, the sampling distribution of p hat. We can approximate that with a normal distribution, which is centered at p, our true parameter value, with standard deviation that we just found from our derivation. And the way that we're going to define large is that we need to check and make sure that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So if I go back and look at these examples, if I have 0.1 times 1, that is not going to be greater than 10, definitely not. If I have 0.1 times 10, that's going to be 1, not greater than 10. 0.1 times 30, that's 3, nope. 0.1 times 50, that's 5, nope. 0.1 times 100, okay, now I'm getting to 10. So that's a big enough sample size. But with different proportions, I can start doing good inference at smaller sample sizes. So if I have p equal to 0.5, 0.5 times 30 is 15, so that's good enough. And then the rest of them are also going to be good. And if I have p equal to 0.7, it'll almost work. 0.7 times 10, that's 7. So that doesn't quite work, but 0.7 times 30, that'll work, and the larger sample sizes will work as well. So this is what we're going to use to approximate the sampling distribution. Rather than doing any type of simulation method, we're going to approximate it with a normal distribution. We need to check these conditions, and the only problem is we don't know p. So that's what I'll be talking about in the next couple videos.